You probably feel like you've got a pretty good handle on numbers. You've got your positives, your negatives, fractions, the whole deal. But what if I told you there's an entire hidden dimension of numbers out there? A dimension that magically transforms messy algebra into, well, beautiful, perfect geometry. Let's get into it. Okay, so we all know the real number line, right? It's our cozy, one-dimensional universe of numbers. It stretches out from negative infinity to positive infinity, and everything from -3 to 0 to pi has its own special spot. It feels complete, doesn't it? Like it's got everything covered.
But is it really? I mean, is it truly complete? What happens when we ask a question that this number line just can't answer?
Check out this equation. It looks simple enough. X squared plus 4 equals 0. Now, to solve for x, we need to find a number that, when you square it, gives you -4. But just think about that for a second. Can you think of any number on our line that does that? Yeah, here's the snag. On that real number line, if you square a positive number, you get a positive. And if you square a negative number, well, you also get a positive. So here's the bottom line. No real number can possibly solve our equation. It's like our number line has a giant hole in it. So to fix this, mathematicians did something incredible. They didn't just find a new number, they invented a whole new kind of number. So let me introduce you to I, the imaginary unit. It's defined simply as the square root of -1. Now, I doesn't live anywhere on our old number line, but with it, boom, our equation suddenly has an answer. Okay, so if I isn't on the number line, where in the world is it? Well, this is the cool part. What if it's not just a new point, but a whole new direction? And the idea here is it's so beautifully simple. You just take a standard graph, with an x and y axis, and you just relabel it. The horizontal axis, that stays as our good old real number line. But the vertical axis, that becomes our imaginary axis. And just like that, we've created a two-dimensional space for numbers to live in.
Any number that exists in this new space is called a complex number. It has a real part, A, that tells you how far to go left or right, and an imaginary part, B, which tells you how far to go up or down. So you see, a complex number isn't just a value, it's an address. It's a specific point on a plane. So now we've got this incredible two-dimensional world of numbers. But how do we do basic math in it? Like adding or multiplying? Well, adding is actually really intuitive. You can think of each complex number as a little arrow, a vector, pointing from the center to its address. And to add two of them together, you literally just stick them head to tail, just like following directions on a map. Walk this way, then walk that way. See? Simple. Multiplication, though, well, algebraically, it looks like this. It's kind of messy, right? It works, sure, but it doesn't give you any real gut feeling for what's actually happening. There has to be a better, more elegant way to think about this. And guess what? There is. The secret to really understanding complex multiplication isn't hiding in the algebra at all. It's in the geometry, and it's all about rotation. Now, to see this, we need to change how we describe our points. So instead of using coordinates like go 3 left, 4 up, we can use polar coordinates. That just means we state two things: the distance from the center, which we call r, and the angle it makes with the positive real axis, which we call theta. And this is the mind-blowing part. When you multiply two complex numbers from this new perspective, you simply multiply their distances and you add their angles. That's it. Multiplication in the complex plane is really just an act of scaling and rotating. Every single complex number holds a secret command to stretch and turn any other number it touches. Now, this whole geometric view, it doesn't just make multiplication easier. Oh no. It reveals a hidden order and a profound beauty in math that was completely invisible before. Let me ask you a really simple question. What is the cube root of 1? You'd say 1, of course, because 1 times 1 times 1 is 1, and you'd be totally right. But you'd only be 1/3 right. You see, in the complex plane, there are actually 3 cubed roots of 1. You've got the obvious one we all know, and then you've got these two other complex numbers. Algebraically, looking at them like this, they look completely random and unrelated. But the second you plot them on the complex plane, just look what happens. They all land perfectly spaced out on a circle.
A hidden pattern just pops into existence.
And what if we connect those 3 points? They form a perfect, gorgeous equilateral triangle. This beautiful, symmetrical shape was hiding inside the number 1 the entire time.
And this is no fluke. It turns out the 4/4 roots of 1 form a perfect square. The 5/5 roots form a perfect pentagon. This incredible pattern just keeps going forever. This all leads to one of the most profound and beautiful conclusions in mathematics. The nth roots of the number 1 will always form the corners of a perfect, regular, n-sided polygon. Complex numbers are the key that unlocks this entire hidden geometric universe. So, what began as just a clever trick to solve an impossible equation ended up ripping open an entirely new dimension in mathematics, one that revealed this stunning geometric structure, connecting basic algebra to perfect shapes. It really makes you wonder, doesn't it? What other secrets are out there just waiting for us to find a new way to look at them